I want you to welcome these guys. They're going to be talking about wrangling internet scale image data sets. Please give them a round of applause.
Okay, so we all know that for any machine learning model, it's only as good as its training data, right? But building a large, high-quality data set of images can be very challenging from an engineering perspective. So today we're going to share some of the lessons we learned, hopefully very practical, that you can take with you in building one of these data sets. My name is Carlos Garcia Jurado Suarez. I'm a machine learning and software consultant for Code Pointers.
And my name is Kieran Merchant. I'm a machine learning engineer for Build Manufacturing.
And this is, before our current jobs, we used to work together at this generative AI startup. And the goal for this company was to build text-to-image models, right? You can prompt with text and get an image out of it. And at a high level, this seems simple. There's open data sets such as Lion, which are pretty big. They're curated. You can download them. So you should be able to take this data set, fit into a model, an existing architecture, and get your model to work. But as you can imagine, the reality is much more complicated. And just to give some context, this was about 10, 12 people in their R&D team, so a small company. So in terms of the outline for the talk, we're going to basically have three parts. One is how do you get the data? And as I said, everything's a little more complicated than it initially looks in that picture. So just how do you get this data? Then we'll go into the semantics of the data curation. And finally, the implementation challenges of actually curating this data. So let's get started. So first of all, I very naively, when I learned about these data sets, and Lion is, if you're not familiar, it stands for Large AI Open Network. So they produce these large billion image data sets. And I thought I was going to find on some website something to download a bunch of images like this. And turns out that's not the case. What you actually get when you download is this. It's metadata about the images. So nobody hosts at large scales images for two reasons. One is cost. Of course, it's very expensive to host such like billions of images. And the other is copyright issues, right? You can't really redistribute somebody else's images that you grabbed, that you basically scanned from the internet. So yeah, that's the first step. You get this metadata, and now it's up to you to actually download it. Luckily, that is not too hard. There's good tooling for this. There's a package called Image-to-Dataset that automates or facilitates this process. You can give it a list of URLs, and it'll do a lot of the heavy lifting from parallelizing the jobs to fetching all these images. But this is when your data curation process starts. Because if you try to just download those billions of images, it's going to take a long time. You're going to struggle with all sorts of data. So you start defining some parameters. And in our case, the main ones were, as you see here in the filtering, the resolution. So we wanted relatively high resolution images of greater than 1024, and aspect ratios that were not too far off from square. So an aspect ratio within those ranges. And you can kick off this process, and what you'll find is that because you're going against the wild internet, you'll get a yield of about 60 to 70% of images will actually download. You get 500s, 404s, 401s, all sorts of little things are gonna get in the way. But once you get all this filtering and you start, you apply this filtering and you get this yield, we were down to about like 40 million images, which is quite a reduction from the 2 billion that this data set starts, but it's still a significant amount of data as we'll see. So now, how do you store this data? So if you've ever worked with millions of files, you know that doing something like this can be very, very slow. Once you have millions of files, you're going to be waiting forever if you try to enumerate all the files in the file system. So you need some alternatives. How do you actually store the data on disk? Or how do you process this data? And we went with a couple of approaches. So imagine this, for every image you have the JPEG and also a text file with a caption, right? So now if you have 40 million images, that's 80 million files. Again, super slow. One of the alternatives is something called web dataset. And if you're not familiar with this format, it's a very convenient format when you have a large number of files. Your data is comprised of large numbers of semantically related files. And without going in all the details, it allows you to pack many of these files into individual tar files. So imagine instead of, if I do 1,000 of these conceptual rows per tar file, now instead of having 80 million files, I have 40,000 tar files. And it's a lot more manageable, and it's a lot more efficient because you do purely sequential I/O. And there's very good libraries for reading, writing, and in particular for consuming these sets of files as PyTorch datasets. So it's a very convenient format to work with a lot of data. One alternative is you can enumerate the files once at least and save a manifest. You basically just save a Parquet file that has all the file names that you have on the file system, along with some metadata. And that allows whatever downstream process you're using to load this file and now know exactly where each data file is and read them. And not as efficient as the purely sequential reading of tar files, but has other properties such as more flexibility. So we used a mix of these two approaches. So now, in this arc of the story, we're down to like, okay, we've got the data. We got the data in a few formats that we can work with. And now Kieran is going to talk about how do we start thinking about data curation.
Nice, thanks. So a lot of the principles of data curation, I think, apply to any type of machine learning training data set that you're working with. But I'm going to be talking about like image text data sets specifically. And I think there's a lot of really interesting nuances with these types of data sets. So in general, formally, kind of what are we working with? Our data set is really, it's a data sequence. So we've got a series of like IID draws from some kind of unknown distribution. In this latex notation, XI is, you can imagine that as an image, and CI is a caption. So like some descriptive text that describes something about the image. Yeah, D is a joint distribution over both images and captions. And I think that if you're in any kind of business context, a really often overlooked but pretty straightforward question is, does the empirical distribution of this sequence that I'm working with, does it align with business needs? If we need beautiful images, are these images beautiful? If we need images with lots of text, do these images have lots of texts? Like at the end of the day, the capability of the model that you're training is going to be upper bounded by what the empirical distribution of your training data set looks like. And if it doesn't, if that's not the case, then we've got, luckily, a lot of training tools to kind of massage this data sequence. And that's what I'm going to be talking about with data curation. So two really main areas of focus. One is filtering with automated metrics. So these can be like classical vision algorithms, but they can also be computer vision models. And then another really essential piece, because CI, that's our caption, is label cleaning. In the image text context, that means typically recaptioning or updating captions with a vision language model. So this is kind of a look at some of the family of like automated metrics that we have available to us. We've got here OCR area is like a metric of what percentage of the image has written text in it. Luminance is a really simple score. It's darker to brighter. And aesthetic score is kind of a subjective, perceptive metric about like the visual or aesthetic quality of the image. And I like these three because they're all motivated kind of differently. Like OCR area, in our case, was really important because the models that we were training, the generative models, didn't do well with text. They produced weird kind of squiggly looking text. So this was one way to kind of control our model output, was to get rid of these text heavy images. Luminance, it was just really common in the literature, and it's fast and easy to compute. And aesthetic score really was about aligning with kind of users' downstream preferences for the model. So I'm going to dive into aesthetic score specifically as a use case, because I think it's really interesting. So what are we looking at here? You can see the first thing you do with any of these automated metrics is you just compute on your entire data sequence. And here you can see distribution of aesthetic scores across our 40 million odd images. You can see it's a fairly normal looking distribution centered at about 5. And on the side, what you see is looking at plotting samples from different bands of these scores. So, things at the top might have an aesthetic score of more like, 3 to 4. You can see there's a lot of text-heavy stuff. There's a lot of like white backgrounds. There's a lot of like weird like graphics and PNGs and stuff like that. All the way down to our higher aesthetic scores, where you're seeing more like beautiful regular images, or like more beautiful artistic images. Maybe you got like a sketch drawing, or like some photography or something like that. And this kind of visualization, this manual digging into the scores, is really essential because you have to understand your score and you need to choose reasonable bounds. So by doing this kind of manual plotting, we were able to see hey, look, we want something above about aesthetic score 4.5, but we're not interested in capping off the top end of aesthetics. One thing that I'll bring up, because I think it's really important, is like when you're processing a ton of data with a ton of automated metrics, it can be easy to get really agnostic about what those metrics are doing. And there's some pitfalls to that. So to get into how aesthetic score works specifically, if you guys are familiar with CLIP, this is a large-scale contrastive model that was trained to kind of bring images and text into a shared embedding space. And when we look at the aesthetic score model, this is specifically the improved aesthetic predictor from a guy named Christoph Schumann. He trained a small MLP on top of the CLIP image embedding to produce this kind of like perceptual quality metric. And every metric is going to have, every automated metric is going to have different limitations. In the case of aesthetic score, we ran into something called the diamond, I call the diamond ring problem. So this is a plot of images with an aesthetic score of higher than 6, and then sorted based on that luminance score that I talked about. And if you'll notice, when we get to the top band of aesthetics, just to zoom in on that, all except for like a few of these photos, you've got some sketch, you've got some like basketball player, every other image is of a diamond ring in this large web scale data set. And so this is why understanding like how a score is computed is really important. In the case of aesthetic score, because it's using this CLIP embedding vector, which is this really kind of semantic vector, it's like really naturally biased towards things, towards images that contain things that you might think of as being aesthetic, like a unicorn or a diamond ring or like a sunset, rather than like really being a perceptual metric on the quality of the image. So that's just kind of the takeaway from that section. A little bit on how you should plot these things, and then understand the model, because it's important for understanding where these scores come from. And just one kind of free plug towards weights and biases. You don't have to use weights and biases. There's a ton of different solutions for this, but like logging and scoring your data in like a centralized platform where you can really like drag through your data is essential. You're going to catch data issues in real time in your pipelines. You can create transparency for your team. You're going to get stronger quality guarantees, and you're going to understand your data more deeply. So I'm just going to talk really briefly on structured recaptioning, and then I'll pass it back to Carlos. Another massive issue with these kind of large-scale image text data sets is that the captions that they come with are really bad. They're like very low quality. So here we have some kind of like Getty image type thing, and you can see the provided caption is "The Ministerial Crisis, a sketch at the Great Western Railway Station, Paddington, Friday, April 23rd, 1880, stock image." So what's wrong with this kind of like open source caption? One, it's noisy. There's a lot of extraneous information like the date. It's non-standard, so the structures of these captions are going to look really different for really different data points. There's a lack of semantic signal. So there's a lot of really important things in this photo that are not covered or described in the text caption at all. And it's misaligned with user preferences. This is not the way that a user is going to prompt a generative model. So through a lot of manual experimentation, prompt engineering, and really just kind of exhaustive testing of different models, we came towards using a model called Lava Next with this following caption. Describe the image in the following structure. Basically, it's broken up into subjects or objects, location, something about the aesthetics, and then something about the camera perspective. And we found that this kind of covered those points that I discussed previously. So just an example, with that prompt, the recaptioning of this image looks something more like the image features 3 men in a room with one man holding a portrait of another man. So you've got subject coverage. The setting appears to be a Victorian-era room with a window and a chair visible. So you've got the background context. The image has a vintage black and white aesthetic with fine details and shading. So you get image aesthetics. And then the camera perspective is from a slightly elevated angle. And just the takeaway from this is like, I think that like this metadata stuff is super common sense. Like if you were a sketch artist and you were asked to draw this image, like by a client, which of these two would you prefer as a description for what you're supposed to draw? These models are much the same. But they don't always work. And this is another big point that I want to drive home with these kind of automated model metrics for data filtration, is there's always going to be failure cases. And unless you're analyzing and plotting your data at scale in a centralized way, you're probably not going to catch all of them. For the Lava Next model specifically, there was this degenerate case where it would just start repeating the same thing over and over again. So like, this image displays a collection of sunglasses, cables, kind of on and on. And then just, again, to plug, how do you catch things like this? You need to use some kind of centralized logging. One last little thing, and then I'll give it back to Carlos, is that these these panel-based solutions are great, but they don't cover all the questions that are going to come up when you're making live decisions in a team. And so we also thought it was really important to build structured database that represented the data we were working with. And so we could kind of like cross-analyze our data in any way that we were asked. How many samples are there? How many have a native distribution greater than 512 by 512? How many have an aesthetic score of less than 3? You really want to be able to answer questions flexibly about your data as they come in. And with that, I'll give it back to Carlos.
I got this. Yeah, so hopefully we've motivated that we need to compute these metrics, right? So, and like Kieran said, some of these are deep learning models. Like the Lava Next model is a fairly big model. Aesthetic score is also kind of heavy. So how do you do this at scale, and how do you compute this for 40 million images? So I'm going to talk about some of the implementation challenges, and there's basically 3 buckets. First of all, how do you properly parallelize? You need a lot of parallelization to do this in any kind of reasonable amount of time. We are often running with 100+ workers, let's say 16 nodes, 8 GPUs per node. You have 128 GPUs going at the same time. You have to be efficient in terms of your parallelization. Robustness, again, with 40 million images, something's going to go wrong. Things are going to fail. You're going to get crashes at the Kubernetes layer, at the QDL level. You need to be able to auto-restart. It's going to be critical. And finally, as you can imagine, if you've done any kind of work on data, you're going to run this a boatload of times for many versions of the code of the data. And you need a way to capture all of this information so you can make sense of your results. So let's quickly dive into each of these areas very quickly. So in terms of parallelization, as I mentioned, imagine now that you have your let's say a Parquet file with your manifest and list all the images. If you launch via Kubernetes, you launch via a job set, a job that creates a container per one of each of these nodes, and then you can use something like torch run to run one processor per GPU. Now you have 128 processes that are going against your data. And as long as you have a nice representation and ordering of your data, each of these nodes can independently decide which rows, basically, it needs to process. So you can very efficiently kind of read in parallel and with very minimal coordination across the workers. Now, for the writing part, what we decided on, and this was actually Kieran's idea, we really wanted to make sure that even though we want everything in one place in the end, we didn't want to have any kind of blocking by having a centralized either database or any kind of mechanism, and again, with as little coordination as possible. So what we did was each of these workers would independently write to a JSONL file, basically just write all your metrics, which is efficient because it's append only. Each one is writing to an independent file, so there's no concurrency problems. And starting to go into the robustness aspect, one little trick we did was that we would write to a temporary file for X number of rows. So let's say every 10,000 lines, we would then rename that file to a JSONL file and start again with another temporary file. And what that gave us was the fact that even if the process crashed, even if the power went out, you knew that any JSONL file that was in the file system was never a corrupted file. We knew there was always, if something had the extension JSONL, it was a complete file and there was no corruption within that file, which will become important in the next slide. And then once all of these processes were done, it was relatively simple to now, like on a single worker, just collect all of those JSONL files into your data Parquet that now had the metadata that you had just computed. So now, how did this help us deal with robustness? So, as I mentioned, being able to auto restart was critical. So this is just the fragment of the YAML for the job set where we were able to say, okay, restart a bunch of times, even the process crashes, right? Because These are expensive GPUs, so if you go to bed, launch a job, and in the morning you find out that it crashes, you're going to be very sad that it didn't make any progress. Right? So we really wanted to make sure that these things were progressing as much as possible. So how did that work? This is kind of, to me, the best way to describe this is to give you this little pseudocode. What we would do is, every time the process started on rank 0, what you do is you look at the file system and say, are there any JSONL files there? And if there are, you bring them, you do this collection process to bring it all into the data Parquet file. You have a barrier that if you're familiar with distributed processing, basically that means all the nodes are going to wait until everybody passes that line of code. Then we read the Parquet file and figure out which rows of this Parquet file are missing that annotation, whatever score that we were computing. Now you have the data, the set of rows that are missing, that are still have work remaining to do. And then you can very easily, if you know your rank and you know the world size, you can easily split the data and figure out which rows you're responsible for each individual worker. And now you can start processing your data. So what this meant was that, let's say there were any kind of crash in the process. If the process restarted, we would automatically pick up where we left from. The only lost work was whatever progress we had made in the temporary file, but any kind of JSONL file we had already written would get kind of ingested. And furthermore, if for whatever reason one of the nodes was perhaps going slower or had some bad images, at that restart point, the data gets redistributed again and kind of the load balance across the remaining nodes, which gave us a lot of also kind of agility in the sense that, again, small company, we had one cluster where we would do training jobs, data processing jobs. And so sometimes we would be running a job with 16 nodes, and then somebody on the team would say, hey, I need 4 nodes, can you release them? We could just kill this job, restart it with, let's say, 10 nodes, and then kind of, we knew that we were not going to corrupt any data. We knew that everything was going to get redistributed across those new number of nodes. So this gave us a lot of flexibility and robustness. And last but not least, so if you were just at the keynote for Databricks, we talked about lineage, right? And it's super important, but here we're talking about orders of magnitude less complexity in terms of lineage, but also in terms of the resources that a small company has. So I'm going to give you the poor man versions of lineage based on Git. What we used to do was we had a tool, we call it IL for the name of the company, to launch any of these jobs. So literally, this is a screenshot of one of those commands. So we'll say, run this annotation job in 4 GKE nodes, 4 Kubernetes nodes, compute the state score. And the first thing that this tool would do was it would write into a shared file, we call it datasets.json, one more entry that, hey, this process is starting, is going to produce this data set. This file was part of Git, so it was now kind of left open in your enlistment, ready to be committed. We would log any command that the tool ran, we would log it in a journal to make sure that everything that we had run to produce had been logged and we knew exactly what command we had used. And then, as you can imagine, this can go into pull requests. So we create a template for the pull request that had some of those aspects that Kieran mentioned, like make sure that you link to the weights and biases run, you make sure that you review some of the images. And because most of the time when you are doing some data sets production, you're going to make some code changes that either allow you to compute whatever new metric you are computing, or maybe some code changes that are required to consume this data set. And the nice thing about it is that the changes to the code, the logging of the command, the logging of the publication of these data sets JSON with the paths, all became part of the one pull request. And then that pull request would go, one of the reviewers would be whoever is going to be consuming this data set. So this was kind of a way of us to just keep track of everything in one location. In our case, Git was our source of truth, and have a kind of a workflow that worked in the setting of our company. And with this, I just want to recap the 3 key takeaways. First of all, in particular for a generative model, really defining and being intentional about the distribution is going to save you a lot of trouble. Right? Second is, whenever you're at scale, design for failure. Whenever you're running locally and testing your code, the code in the try is going to run, but you run at scale, the code in catch is going to run a lot more. So plan for that. And finally, what I just mentioned, like log and version as much as possible. And I have some mechanism by which you can track that. Because once you're downstream and training and doing something more complex, if something goes wrong, being able to track back where everything came from is really going to save you. We used to call it, we need to save the receipts, right, for any kind of data that we produce, so we could track back to any type of problem. And with that, thank you. This is, here's a couple of links to we wrote a paper, and then also that data set is published on Hugging Face, if you want to play with now a smaller set of images that have been more filtered and higher quality. Thank you.
Thank you.
Yeah, there are questions. We're happy to.
Hi, I was wondering, you mentioned that you can look at some of the data on weights and biases, and then I saw, you were using a lot of automated stuff to produce these charts of some of the images and stuff. And I guess in 40 million images, I was wondering, was there anything else? Because I'd imagine there's a lot of garbage that you might not have picked up. Did you have a scroll bar? You're scrolling and just seeing random pages and have a lot of humans kind of reviewing, and did you find anything interesting in there?
Let me answer the weights and biases, and then I'll pass to Kieran for the other part. So for the weights and biases side, what we would do is, whenever one of these metrics was being computed, we would do automatic stratified sampling. So we would sample at every kind of range within the distribution a configurable number of images. And of course, that's going to be a subset, but that was kind of more in real time, as your data is starting to run, you're starting to see what images of this kind of bucket will look like. But then Kieran looked a lot more closely. So.
Oh, yeah, I was just going to say, yeah, and then I just looked through, like, thousands of images. Yeah, yeah.
And I think that's part of the point with these metrics is that initially, if you have no metrics, or there's no axis for you to explore the distribution. All you can do is, like, look at images, right? Once you have some axis, like OCR, well, the ones that we mentioned, aesthetic score, luminance, and we did this for video, so you have, like, motion blur, and like a bunch of other metrics. Now, it gives you some way in which you can slice your data in some semantic way.
Yeah, great work. Thanks so much for the presentation. I hope this is not too much of a tangential question, but I think I heard that when the text was being generated on the images, I think you mentioned that they were sort of, I guess, squiggly visuals per se. And I was sort of curious, I think, like, quite an old paper that came out a while back was something along the lines of conditioning the data generation process of the models itself. For example, models like pix-to-pix, more like GAN-based models, not on diffusion work per se. And how would you envision something? I know this may be like a totally new experiment, but just in terms of your thoughts and, like, how we might be able to sort of condition the data generation process now with this new family of models per se.
I think that, like, in the last year, labs have done a phenomenal job at some, like, interesting, unique conditioning strategies to kind of inject information and signal from the text at different layers of the architecture. But I think that even in the largest labs in the world, it's an auxiliary thing. It's something that needs to be accounted for, like, post hoc.
And one thing I'll add is, I think when it comes also to your distribution, what we found is you need to kind of empirically find, based on your resources, like your number of GPUs and even people that you have to select how wide of a distribution can you really model and kind of start to adjust for that.
So, sort of a quick follow-up question. So, like, have you tried sort of trying to interpret why might that be happening? Like in terms of just trying to understand the underlying mechanism of the model itself, more from an explainable AI perspective? Just curious.
I mean, I've got theory. Yeah. I mean, I think in our specific case, because these models are trained with some kind of like a VQVAE or some kind of compression model, you're losing a lot of that, like, finer grained signal, and text falls into that category.
Yeah, and if you just remember did you have the plot of the OCR scores? Maybe not.
Oh, no, I did not.
Yeah, but so if you look at the static score, it's a nice normal distribution. If you look at the OCR scores, it's like most of the data has no text, and there's a big tail of like a little bit of text. So there's also a data scarcity problem in there.
So just curious about the diamond ring problem. Did you see the problem start emerging at lower aesthetic scores? And if it was really just concentrated at the top, would you get a more realistic aesthetic score if you just, like, clipped the top 10% as just, this is diamond rings, throw them out? and then rescaled the score.
Yeah. The diamond ring problem only showed up in the very top bands, but because it was a pretty equal banding, throwing them away would have meant discarding too much data, basically. So we thought it was more important to kind of preserve that high aesthetic score data, even if it was biased as described.
Thank you for the presentation. It's very insightful. I'm just wondering, how did you end up with weights and bias? Have you tried other frameworks? I think there is a bunch of open source softwares available. Have you tried any others?
Yeah, I worked with MLflow before. The ones that I knew were weights and biases and MLflow. It's a typical buy versus build, or like in the case of an open source reuse. Honestly, when we explored weights and biases, we first tried deploying the open source version of our own. It worked, but then just judging by cost, how much will it cost for weights and biases, the team to manage it for us, a private instance, I guess the benefits outweighed the cost to have just a platform to be managed for you. If you only have 10 people in your team, you really want them to be focused on the machine learning research and the specific problems that you can solve. So yeah, it was more of a decision around costs and benefits.
What is the cost about? Is that about the using of the GPUs, or is it about the cost of the platform? The
platform. So if you buy weights and biases, they have a few different deployment models. So you can, as I said, you can get the open source version and just run it on your own, or you can have them deploy an instance for you that is private to you, and they'll manage it for you. And then, of course, that has higher costs. It's basically a per user seat license. And in our case, we thought that it was worth it, the price.
Have you ever used the NVIDIA's NeMo curator to curate the image and the video?
No, we've heard of NeMo, but we have not used it, no. I know you have, no.
For the video, it's just fully released, and for the image, it's being released as open source. So maybe you can share your experience after you try with me.
Yes.
I can
Next
get
year.
back to the engineers.
There are no more questions. Let's thank our speakers again, Karen and Carlos. Thank you.
Thank you.